So actually, in the previous session, we have come across a matrix. Let me write the matrix once again. The matrix was given as this: 1, 1, 1, 2, 0, 1, 1, 3, 2. And we are supposed to find the rank of the given matrix, to find rank of the matrix, rank of A. So what we did, we transformed the matrix. If I write the what is written in the book has transformed the matrix one transform the matrix A into this form: 1, 0, 0, 0, minus 2, minus 1, 0, 2, and 1. Okay. And after that, the book has declared that these two columns, actually are linearly dependent, and therefore number from there they have directly said that in this particular matrix there are two linearly independent columns, and therefore rank of A equal to 2. But I actually proceeded a little bit further, and I showed you that after applying several column and row operations together, we can get a matrix of this form. Okay. So question is, and then I said that I named this matrix as B, and I wrote that, yeah, it is clear from the picture that rank of B equals to 2, and therefore it must be equal to rank of A. So that is what I did in my previous session. The question is why? So someone can ask that if I can declare about rank from this matrix, intermediate matrix, so why do I proceed further to the given, to the form which you have shown in the previous session? The form which I have shown over here, this particular form, in some books, you will come across that this form is called normal form. It is called normal form. And what is the objective of this particular form is that, say, for example, if you have the book of S.K. Mappa, there they have discussed, probably they have discussed, I cannot recall right now, that this type of form which is obtained by applying row and column operations together, elementary row and column operations together, are called normal forms. And after this normal forms, what is my objective actually? My objective is actually to bring, my objective was to bring as many zeros as I can, as many zeros as I could, as many zeros as I could. Okay, so if you can bring as many zeros as you can, that would be, that would be eye soothing, and you can easily say that you can easily count the number of, number of columns, independent columns, very easily. Okay, so that's why I did this. I did this also by keeping in mind another theorem which is there in the book, and I'm going to write it. The theorem goes like that. What is the theorem? The theorem number is 3.6. The theorem says, let capital A be an M cross N matrix, okay, of rank R, of rank R. Then R less than or equal to M, R less than or equal to N, and by means of a finite number of elementary row and column operations, capital A can be expressed, can be transformed, capital A can be transformed into the matrix into the matrix, capital D is equal to IR O1, O2, O3, where O1, O2 and O3 are zero matrices, thus thus dii is equal to 1 for I less than or equal to r, and dij is equal to 0 otherwise. This theorem is written just below the matrix in the book. Now let me connect this theorem to the given normal form which I have obtained. Okay, and you will understand why did I transform the given matrix into the normal form. Because I wanted to apply theorem 3.6 over here. If I want to connect theorem 3.6 to the given normal form, then you will get to see that in the matrix, the rank has come out to be 2. And originally the matrix has order 3 cross 3. So here m is equal to 3, here n is equal to 3. So both are same, so it is a square matrix. Now since rank of the matrix is 2, so we have got rank which is equal to r. If I want to relate this uh, theorem with the given matrix, you can easily say that 2 is actually less than 3, r is less than m. Again I am writing 2 is less than 3 as r is less than n. So here I am writing 2 less than 3, it's because r is less than m, and here I am writing 2 less than 3 because r is less than n. Here m and n are same actually. Okay, and now they have said that after performing a finite number of elementary row and column operations, you can transform the matrix A into a matrix of this form, capital D. So this B, the matrix B is actually my capital D. You see, I have transformed the matrix in this form. So this matrix is actually my, what is that? It is actually my IR. So according to the theorem, this matrix is my I2, which is an identity matrix 0, 1, 1. Okay, and this matrix O1 is represented by this column matrix. So here O1 is actually the column matrix 0, 0. This matrix is my row matrix, so that is O2, that is 0, 0, and this is a matrix all single row, one row and one column, that is my O3, that is 0, only 0. So I have actually transformed the matrix into the form IR O1, O2, O3. That form is actually, in some books, they call this form as normal form. Okay. And here it is written that dii equals to 1, I less than or equal to r, I less than or equal to r. So if I consider d means the entire matrix they are talking about. So diagonal element of this D matrix. So if you see here in this matrix, D11 is equal to 1. And why it is so? Because 1 is less than 2, I is less than R. Okay. D22 is equal to 1. Why it is so? Because 2 equal to 2, I equals to R. And other elements are 0 over here. D33 is 0. Why D33 is 0? Because 3 is not less than 2. And other elements are 0 by the rule, Dij equal to 0 otherwise. Okay, so everything you can connect this particular theorem to the given problem which I have shown over here. And therefore, I have tried to found the normal form of the given matrix. So from here also you can say that this matrix is linearly independent. These columns are dependent and it has two linearly independent columns. But I shall suggest you always to always try to find out the normal form before you declare something about the rank of the matrix. Okay, and this theorem therefore is very important, so just keep in mind. And one more thing I must say, probably very few students will finish the book of Friedberg, uh, but others, if probably, since okay, you are computer engineering students, probably you are not so much uh, attached to maths, so therefore to them probably they will not get to see what is written in the last chapter of the book. This type of matrix capital D, which I have got over here, IR, this matrix, inside the matrix you have got another matrix. So I got actually like this is a matrix, this is a matrix, this is a matrix. I got things like this. Okay, so this is called, actually called block matrices, block diagonal matrices. So those who can reach up to the last chapter, they will be able to find know that why block diagonal matrices are very important. So right now you can skip it. I'm just telling you for the sake of just like that. It has nothing to do with my current topic. Now you can ask me that why do now your question can be, why do we need to find rank, rank? Okay, so don't think that this answer will be, this answer has already been stated. I said that rank of the linear transformations, if you cannot find the rank of the linear transformation directly, then indirectly rank of the linear transformation can be found by the rank of its matrix representation. That doesn't mean why, that doesn't answer to the question why do we need to find rank. Why do we need to find the rank of linear transformation at all? If someone asks, what should my reply? Okay, so the basic objective is to know the basic objective for which we actually are interested about rank of linear transformation or rank of the given matrix is because the answer is we want to test whether the matrix has inverse, whether the matrix has inverse. Now if you ask me why do we need to find the inverse of a matrix, then the answer to the given, now the question is, since I have actually muted disabled the chat box, so I am writing your question on behalf of you. Why do we need to find inverse of matrix? Then the answer to the given question is to solve system of equations. So if you have a system like Ax equal to b, and you already know that this can be written as A inverse B if A inverse exists. Okay, you know this. And a student who is repulsive towards maths, if he asks me why do we need to solve system of equation, then I have nothing to say. This is the answer. So so therefore this is the reason for which we actually are interested about rank. Now If we talk about, suppose I'm considering this this linear equation ax equal to b, and you know that this equation can be written as x equal to a inverse b. If a inverse exists, one of the criteria by which this can be done is uh, that we first check we first check we first check whether determinant of a or det of a is non-zero or not. If det a non-zero, if this is true, then we say that A inverse exists. If this is true, we say that A inverse exists. Now, if the matrix, suppose if the matrix is of order 2 by 2 or order 3 by 3, then easily you can find determinant. We are familiar with this particular calculation. If the matrix is of order 4 by 4, then also we can find determinant using Laplace transformation, Laplace expansion, not transformation, that is different thing, Laplace expansion. Now, this topic was used to be in the syllabus previously, but now this topic has been removed, Laplace expansion. Now, suppose if I consider a matrix of higher order, I can consider a square matrix of order 5 or square matrix of order 6 or anything, a square matrix of order n. Then how do you know that determinant? How can we tell about the determinant? Then it becomes the calculation becomes so complicated, and therefore it is not like that the determinant of square matrix of order n cannot be found. Everything can be done, everything is possible in mathematics, but the calculation becomes very tedious, and therefore actually uh, you can say that there are some limits in applying the determinant criteria to the matrices to know about its inverse. So here comes rank as a savior, and the rank says that result is there in the book. It is written, you can find it. I'm not going to say in which page it is written, but you have to find it out by yourself. So it is written like this. It's a result and n by n square matrix, and n by n matrix is invertible if and only if its rank is n. An n by n matrix is invertible if and only if its rank is n. Now, what matrix we had worked with just now? We have worked with this matrix. Okay, so let me write the matrix from the book once again. Our matrix was the matrix which we have considered was capital A 111 201 132. Okay, and we have come across that we have found that rank of A is equal to 2, which is not equal to 3, the order of the matrix. Order order of the matrix not equal to, or what is the order of the matrix? It is 3 by 3. Therefore, by this rule, the matrix A has no inverse. Matrix A has no inverse, or A is not invertible. A is not invertible. I am enabling the chat box and I am asking you to find determinant of A, and if you want to test what I have told you just now, find determinant of A, you know it how to do, and tell me what is the value. And believe me, without testing, don't believe me. Okay, so try to find quickly what is the date of A, and then tell me that yes, you have agreed with what I have said just now. So so what have we come across? We come across that in this particular matrix, the matrix rank is uh, not equal to the order of the matrix, and therefore the matrix is not invertible, and it exactly goes with the criteria of testing whether inverse exists or not with the help of determinants. And we have also seen the determinant of this particular matrix is also 0, so it justifies the fact that yeah, we are on the right track. Now gradually you are seeing that probably you have noticed that I am in this particular class, I am not mentioning the frequency of uttering the word vector space, vector space, vector space. For the last couple of months, you have listened to this word vector space several times. So probably you are just tired of it. So gradually, actually, the discussion about vector space is being minimized. The number of times, the frequency of uttering the word vector space has been minimized. Okay, and we have now going into the details of matrix operations, and uh, rank and everything will be discussed on the basis of matrix. So that, because we are now in module 2 and module 3 is done, but on the back of the mind, never forget vector space, because whenever you work on matrix, always remember that this matrix is actually connected to whatever matrix you are working with, is always connected to some sort of linear transformation at the back. So don't forget that. So I think that probably now you are happy that at last we are free from vector spaces. Okay, so anyways, now let me put another definition which is also important for discussion of our current topic. That definition is of augmented matrix. Okay, so let's try to know what this definition is. Let capital A and capital B, I am I mean, when I teach, actually, you may, at first you may feel that sir is so scattered. His thinking is so scattered. I mean, sometimes he's saying about rank, and then previous he started with linear transformation in rank, and then suddenly he has written so many theorems on the screen, and right now I'm going to give you the definition of augmented matrix. So probably some of the students are thinking that sir's thinking is so scattered. Now, don't think like that. I'm not scattered. I'm well organized in my mind. Everything will be summed up, just like we summed up things just a few minutes ago regarding rank, etc. Augmented matrix, I'm going to give you the definition of augmented matrix. I'm going to sum it up at certain point of time, because everything is connected to every other thing. If you read this chapter carefully, section 3.2, you will see that many a times they have said that, yeah, to prove this, we have used the result from page number 100, and that result from section this, and that result from this exercise, several times. Because everything, if you move on with the book further and further, you will see that this particular line has increased in number. We have used it, we have used that from that particular page, etc., etc. Okay, so everything is connected. So let me give you the definition, then I'll try to gradually connect everything with you. You may probably are thinking that why suddenly in the discussion of augmented matrix, without giving us any problem, he has, in this discussion of inverse of a matrix, without giving us any problem, he has suddenly moved into the definition of augmented matrix. Is the discussion of inverse matrix is complete? No, no, it is not complete. I shall come to this point after some time. Let capital A and capital B be m by n and m by p matrices. Okay, respectively, by the augmented matrix, which we denote by A vertical bar B, we mean the m by n plus p matrix AB, that is the matrix whose first n columns are the columns of A and whose last p columns are the columns of B. Are the columns of B. I am enabling the chat box so that you can put your attendance because the 8 minutes 38 seconds left for this class. Now, augmentation. What is augmentation? Augmentation is a kind of addition. This addition is not in the sense of matrix addition. This addition is in the sense of consideration. So, for example, if you have a matrix like this, say for example 1 1 2 1 or 3 2 like this, and another matrix you have of this form 1 2 2 1 like this. So order of this matrix is how much? 2 by 3, and the order of this matrix is 2 by 2. So if I want to augment the two matrices together, then I must write it in this manner because this is the notation, and we must write that 1 1 3 2 1 2. It would be nice if you put a vertical bar just to make sure that you are augmenting things, and 1 2 and 2 1. Now you see what is the order of this matrix. This order of this matrix is 2 by 5, and this can also be written as 2 plus 2 cross 3 plus 2. So you see that this first 3, this number 3 is actually the number of columns present in this matrix, which is n, where n equal to 3, and number 2 is the number of columns present in this matrix, which is n equal to 2. Okay, so that's how we actually augment things together. And if you want to ask me that why augmentation is important for two purposes. Probably once I told you in my last class why augmentation is, I can recall that once in my session, one of the sessions, I used the term augmentation once. But later I shall discuss augmentation in details when we'll come across the solution of system of homogeneous and non-homogeneous equations. Also, augmentation is very important for I mean for finding inverse matrix. So what we do actually is that we are going to, why it is important. So suppose a matrix is given to you. Okay, so suppose a matrix is given to you. Many things are written in the book, so I'm giving you the strategy in very brief, so in my style, so that you will find it easier to understand. So suppose a matrix is given to you. The matrix is denoted by capital A. The matrix is capital A, and suppose you know that A is invertible. That is, rank of A is equal to order of A. Rank of A is equal to order of A. Suppose you know that. What we do that is that we augment the identity matrix with the given matrix, identity matrix of same order, and we want to apply elementary row and column operations, elementary row and column operations, okay, and try to find out an augmented matrix of this form. So actually by this, if we can transform the matrix A into the matrix I, and if you can transform the matrix I into the matrix B, in that sense, in that case, we actually say, if we can do this, we say that A is inverse of B and vice versa. So previously you used to find the, you actually to find the matrix, what did you do? You when you check that determinant of A is equal to, is not equal to 0 and A inverse exists, okay, then you use this formula to calculate A inverse. Adjoint A, which is the transpose of the cofactor of the matrix by determinant of A. Okay, now I am telling you that, yeah, this some problems you can use this particular result, but if the matrix is of higher order, then determinant actually is not helpful very much. So then you can apply again, you can apply that this results which I have written over here to find the inverse of the matrix. So totally, the inverse of a given matrix is totally dependent upon the elementary row and column operation, and a the way by which you can bring it to the normal form. I mean, if you can do it properly, if you can transform AI into IB, then that in those, through these operations also the inverse of the matrix can be found. Okay, so therefore it is very powerful. So what was my matrix? The matrix whose inverse actually didn't exist. That matrix was 1 1 1 2 0 1 1 3 2. Okay, and suppose you can ask me one question, sir. First of all, if the matrix is too long, then I have to find we have to find the matrix representation. First of all, you have to find by elementary row and column operation whether inverse exists or not, and after that again we have to find matrix representation, again rank operations to find inverse. Yeah, little bit clumsy but helpful. So suppose you do not know whether the inverse of the given matrix exists or not. So the process is, if you try to do it directly, so you are connecting A with the matrix I and try to apply the same row and column operations, and you can see that what will happen, what comes, some absurdity will come, because you already know the inverse of the matrix doesn't exist. Okay, this session is going to end. Next session will start after 5 minutes. Okay, in that session I ask everyone to be present, because I'm going to show you something very interesting. Okay, for the first time. So, and meanwhile, take a rest for 5 minutes and then join just after 5 minutes, and then you are, meanwhile you can try this particular problem and you can check whether indeed what is happening over there. Okay, so I'm pausing my video over here, and then after 5 minutes I'm going to again restart my session, last session of my today's class.